Today we will discuss universal Turing machine. First of all, we will discuss what is Turing machine and what are the limitations of Turing machine. So first, the limitation of Turing machine. Turing machines are hardwired. They can execute only one program. They can be designed for only one program. But real computers are reprogrammable. We can execute more than one program for the same computer. So we can say the Turing machine is as powered as the real computer. Yes, we can say. The problem the solution is the universal Turing machine. So universal Turing machine attributes are reprogrammable machine, and it can simulate the other Turing machine. Next, Turing machine, universal Turing machine simulate any other Turing machine M. The input for the universal Turing machine will be the description of the transition of the Turing machine M and the initial tape contents of the Turing machine M. We use three tapes in the universal Turing machine: tape 1, tape 2 and tape 3. Tape 1 is used for the description of the Turing machine M. Tape 2 is used for the tape content of the Turing machine M, and third, tape 3 is used to state of the Turing machine M. First, we will discuss what will be the description of the Turing machine M. We describe the Turing machine M as a string of symbol. That means we will encode the Turing machines as the string of symbols. To encode the symbols, suppose we have the alphabets. Suppose alphabets are A, B, C, D, and we can encode it like A we can encode as 1, B can encode as 1 1, C we can encode as 1 1 1, and D we can encode 1 1 1. Same way, if we have E symbols, then we can encode 5 times 1. Next, we have the states of the Turing machine M. State Q1, suppose we are encoding as 1, and state 2 we are encoding as 1 1, and state Q3 we are encoding as 1 and state 4 we are encoding as 4 times 1. And one additional thing we have in the Turing machine, that is known as the head movement. If head movement is in the left hand direction, we can encode by 1, and it is moving in right hand side, we can encode as 1 1. So if we have any transition functions, how we will encode up this transition function into the string of 0 and 1. So we can see here we have the transition function delta q1 comma a and equals to q2 v comma l. We have already seen the code for q1 is 1 and the code for a is 1, and code for q2 is 1 1, and code for b is 1 1, and code for l is 1, and in between all we are using the 0 as a separator. So if any transition function is given, we can encode complete transition function as a string of 0 1. Here 1 is the encode and 0 we are using as a separator. Now if we have more than one transition functions, so we will encode all the transition function and to combine them by using the separator 2 times 0. So in this example, we can see here we have two transition functions, and 0 0 we are using as a separators to combine these two transition function. That means tape 1 contains the universal Turing machine. That means we have the encoded Turing machine M, that is in the string of 0 and 1, and we can simulate this Turing machine on universal Turing machine M. In this way, if we have more than one Turing machines, what we can do, we will form a language. That means set of Turing machines form a language. That means each string of the language is a binary encoding of the Turing machine. So if we can see here we have the Turing machine 1 2 3 like this. We have the language L, and all the strings are in 0 and 1, and we can see here all these are the Turing machines. So in this way, any Turing machine we can simulate with the universal Turing machine, and the universal Turing machines will be as powered has the same power as the universal Turing machine Now we will discuss about the countable sets. Countable sets are countable sets may be infinite or it may be a finite. So set, if we have any set, that may be a countable and uncountable. So here in this lecture we will discuss the countable set. So formally we will define the countable set as any infinite set is known as the countable set, and any countably infinite set, if there is one-to-one correspondence between the element of the set and the natural numbers. We will take some examples of the infinite set. So the first example we will discuss here, the set of even integers, that is countable. We will see here we have the even integers 0, 2, 4, 6. This is the set of even numbers, and we can see here we can provide the correspondence with these even numbers to the positive number 1, 2, 3. That means we can count them, we can provide the correspondence, so it is countable. Now another example, we will discuss the set of rational number. We will check it is countable or not. We can see here in the screen rational numbers. We have 1 by 2, 3 by 4 and 7 by 8. All are the rational numbers. So we will prove that we have the set of rational numbers and we are able to provide the one-to-one correspondence or not. So we have rational numbers whose nominator is 1 and denominator is 1, 2, 3. If we are basing approach for denominator 1, we can provide the correspondence, but it will not work if we have denominator 2 or denominator 3 and so on. So another approach we will discuss to prove that the set of rational numbers is a countable set. So we have in first row we can see here we have the denominator 1, and in second row we can see here denominator is 2, and in third row denominator is 4. What we will do here, we will check rational numbers can be represented as p by q, and what we will do here, p plus q we will find out. And suppose my number is 2, 3, 4. I will take all the rational numbers whose p divided by q sum is 1. So first I can take 1 by 1, then I can take 2. So rational numbers related to this one, 1 by 2 and 2 by 1. These are the rational numbers related to the sum of p plus q equals to 3. Next we have 4, then 1 by 3 will be there, 2 by 2 will be there, and 3 by 1. These are the rational numbers of the sum p plus q equals to 4. So in this way we will provide the correspondence like this. First we will take 2, then some 3 value, then some value 4. In this lecture, 1 by 1 we will consider first, then 1 by 2 we will consider, then 2 by 1 we will consider, then 1 by 3 we will consider, then 2 by 2, then 3 by 1, and so on. So we can say we can provide the one-to-one correspondence between the rational numbers and the positive integers. So we in this way we can prove the set of rational numbers will be set of rational number will be a countable set. That means to prove rational numbers is a countable set, we use the enumeration process. Thank you so much.